Today we are explaining seeds self-evolving on policy distillation for Agentic reinforcement learning. The paper asks how an agent can learn from the useful decisions hidden inside a completed interaction, even when the environment gives only one reward at the end.
What is the central learning problem when an agent has to act for many steps before it knows whether the task succeeded?
In a long horizon test, an agent may inspect several observations, photos, and make many decisions before receiving a success or failure signal. Outcome-based reinforcement learning sees the final result, but that result does not say which individual token or action helped. Seed turns the completed trajectory into a natural language hindsight skill, then distills the skill's behavioral effect back into the ordinary policy.
Why is a single reward at the end not enough to teach the agent what to do differently next time?
Standard group relative reinforcement learning broadcasts one advantage across every valid token in a trajectory. A successful episode can contain inefficient choices, and a failed episode can still contain a useful local decision. When all sampled episodes have the same outcome, the reward-based advantage becomes zero, so the outcome signal cannot distinguish those local choices at all.
Could an agent simply write a useful skill into the prompt and let the model follow it?
Prompting helps only if the skill is supplied during inference, which adds context and does not change the policy itself. Other methods train with skills but remove them at evaluation, or add a generic self-distillation loss without using the completed trajectory to decide which tokens the skill supports. A static skill library also becomes stale as the policy changes its behavior and its failure modes.
So what changes in seed that makes the guidance both useful and reusable during training?
Seed has the stages. First, it collects ordinary offline trajectories and fine-tunes the policy to analyze a completed interaction and write a hindsight skill. Second, the same evolving checkpoint plays to rows. An actor collects fresh on-policy trajectories, and an analyzer reads each completed trajectory and extracts new guidance. The skill is used to create a training signal, not to change the deployed prompt.
What does the analyzer contribute that the acting model could not get from the final reward alone?
It can inspect the whole interaction after the outcome is known. For a successful trajectory, it may describe a reusable workflow or a decisive observation. For a failed trajectory, it may state what to avoid or what correction would have prevented the failure. This turns hindsight into a concrete behavioral description before the policy update is computed. After the update, the new checkpoint becomes both the next actor and the next analyzer. That shared refreshes the self-evolving part of seed. The policy's behavior changes. The trajectories its ease change. And the skills it can write change with them.
How does a natural language skill become a dense signal for individual action tokens?
CD keeps the action that was actually sampled. It scores those same action tokens twice with the current policy. Once under the ordinary interaction history, and once after inserting the generated skill into that history. The difference between the two log probabilities says how strongly the skill supports that particular token in that particular state.
What does that probability shift do for each token?
The gate is a sigmoid of that shift. If the skill makes a sampled token more likely, the gate becomes larger and the auxiliary supervision strengthens. If the skill makes the token less likely, the gate attenuates its contribution. So seed does not treat every token in the trajectory as equally valuable.
How does that token-specific weight enter the policy loss?
The OPD loss is a gate-weighted negative log likelihood on the ordinary policy branch. The skill-conditioned log probability and the gate are detached, so gradients update the ordinary policy to raise the likelihood of the tokens endorsed by the skill. At deployment, the policy can therefore use the learned behavior without an analyzer, retrieval system, or extra skill prompt.
Does seed replace outcome-based reinforcement learning, or add the signal beside it?
It combines them. Group relative reinforcement learning still optimizes the environment outcome and keeps the KL regularizer. The OPD term adds token-specific hindsight credit, weighted by lambda. The updated policy then supplies both the next rollout distribution and the next analyzer, closing the loop between decision-making and skill analysis.
What tasks and comparisons test whether that extra supervision matters in practice?
The experiments cover 3 forms of long horizon interaction: household tasks in ALF World, web navigation in WebShop, and search-based question answering. The baselines include a frozen prompting method, outcome-only reinforcement learning, generic on-policy self-distillation, and skill distillation methods. Evaluation removes the skill prompt unless a baseline is explicitly marked as using one. The main comparison shows seed at 91.8 on ALF World, 45.7 on search-based QA. The corresponding GA RPO scores are 75.0, 36.4, and 63.3. Seed is also above skill prompt on every aggregate metric, and it beats skill GA RPO with a test time skill in 11 of the 12 aggregate comparisons.
So the advantage is not just from giving the model more text at test time. How much does the learn policy improve over the outcome-only baseline?
On the three aggregate metrics, the gaps over GA are POR 16.8 points on ALF World, 9.3 points on search-based QA, and 15.6 points for webshop exact success. The important comparison is that Seed keeps those gains while evaluation uses ordinary interaction history, so the skill has been internalized rather than merely appended to the prompt. The training curves explain how that difference develops. With the Q into 0.53 billion instruction tune backbone on ALF World, Seed reaches roughly 0.89 episode success by the end of training, while GARPO is around 0.77. Seed also finishes episodes in about 12 to 13 turns rather than roughly 15 to 16, suggesting both more successful and more direct behavior.
Does Seed reach that level of performance with the same amount of training data as GARPO?
The sample efficiency plot says no. With only 60% of the training data, Seed reaches an 80.7% success rate, while full data GARPO reaches 75.0%. That is a 5.7 point advantage for Seed despite using 40% less training data in this comparison.
Is the improvement spread across household tasks, or does one category account for most of it?
The ALF World breakdown shows gains in 5 of the 6 categories. Seed improves over GARPO by 16.5 points on pick, 18.3 on look, 35.0 on heat, 13.5 on cool, and 11.3 on pick 2. Clean is the exception, where Seed is 2.9 points lower, averaged across categories. The qualitative comparison shows what a local credit signal can change. For the same request to put a candle in a toilet, the GARPO trajectory searches the wrong places, repeats actions, and never secures the target. The Seed trajectory notices that the candle is not in the initial view, searches plausible locations, finds it on a shelf, and then places it in the toilet.
What happens if we remove parts of the method, rather than using the full combination?
The ablation isolates 3 ingredients on ALF World. Removing the initial hindsight skill supervised fine-tuning drops the average from 91.8 to ITXS points IRO, or 5.8 points. Removing self-evolving OPD drops it to 87.0. Replacing fresh on policy skills with a static offline library drops it to 84.4, the largest loss at 7.4 points.
Why does the paper insist that the skills must come from the current policy's own trajectories?
The theory gives a precise reason. At the current policy's visited contexts, the expected OPD update is equivalent to distilling toward a target distribution that reweights actions according to how strongly their hindsight skill supports them. Old trajectories change that context and action distribution, so they can bias the auxiliary update in proportion to the mismatch between old and current data. On-policy collection removes that rollout mismatch.
Can the OPD signal still help when every trajectory in a group receives the same final outcome?
Yes, provided the skill gate is not identical for every candidate token. In the tied outcome case, the group relative reinforcement learning advantage is 0 for all tokens. But the skill conditioned ray scoring can still assign larger support to some decisions and smaller support to others. That gives Seed local credit exactly where terminal reward has gone silent.
What prevents the analyzer from becoming outdated while the actor keeps improving?
Seed refreshes both roles from the same current checkpoint. The paper's synchronization analysis bounds the change in the auxiliary update by the change in the analyzer skill gates. And the shared refresh makes that cross-iteration analyzer mismatch 0 at rollout and analysis time. In plain language, the source of hindsight evolves with the policy it is meant to improve.
What is the shortest accurate summary of the paper's contribution and evidence?
Seed separates acting from hindsight analysis without separating their parameters. It uses completed on-policy trajectories to write skills, converts skill-induced probability shifts into dense token supervision, and combines that signal with outcome-based reinforcement learning across household interaction, web navigation, and search-based question answering. It improves aggregate performance, reaches higher success with fewer samples, and keeps the gains without a skill-prompted inference.
So the key idea is to let the policy learn from what its completed behavior reveals, while keeping the deployed agent simple.
Exactly. Seed makes hindsight supervision self-evolving, on policy, and specific to individual decisions. That wraps up this paper explanation.